Either way, your professor covered the exam today. How do you feel about it? Do you feel like it was a fair exam? Uh, Overall, I saw the average. It was around a 61 or so. Only two people got 100. From what I saw, it was a relatively fair exam from my perspective. But again, I've been doing this for a few years, so I'm getting really comfortable with his testing style. So if you didn't get the best grade, that's okay. Just the first one. You're getting used to how he's writing down the questions, condensed formula. Now you guys know that it's very important. But either way, if all of you already scanned the QR code, let's get started with chapter 13. Oh, what happened? Okay, we're good. Okay, so actually, your professor was talking about this theory today. And actually, we started our discussion on this last time. We were talking about the molecular orbital theory, the pi bonds, and all of that, right? Really quickly. How do we know that we are using the theory? Why do we use it? What does it tell us? What does molecular orbital theory tell us? What's it? Yes. Now, what kind of questions could he ask you? That's a great question. Yes. So today he was talking a lot about the theory behind the orbitals and all of that, the transitions. You guys are not really gonna get asked questions on how the orbitals look like, all of that. You're just gonna get asked simple questions like the ones that I told you guys about in last session. For example, how many electrons do you see in the LUMO orbital and the excited state? Things like that. They're gonna be pretty straightforward, and that's why the tables are provided for you guys. Pretty much you can just memorize that part, but of course I'm gonna teach you how to actually do them on your own. So last time we were talking about a diene. Pretty simple. Do we have any questions from that one from last time? 1, 3, 5. Pretty simple. So far so good. We remember it. Question. Yes. It's always gonna be from HOMO to LUMO. And actually that's gonna be the most favorable transition, and you might get a question on that. Yes. Mhm. Mhm. The UV light. Exactly. No, no, no. He's not going to be asking how far up. The only thing he might ask you is what's the most favorable transition. So the answer is always going to be HOMO to LUMO. So in that case specifically, it would be from pi 2 to pi 3. Things like that. He's just going to give you that transition. He's not going to ask for the how long is the jump of that. We jump one of the electrons to the LUMO because we're excited. The excited state is just something that's temporal. What's actually in the molecule present on its own, the light, is going to be the ground state. That's when we find out the home on the LUMO. There's a LUMO in the ground state, there's a home in the ground state. The only thing that happens when the UV light hits it is that it's going to excite one of the home electrons up to the LUMO electron. And yes, technically, we can see that the home is going to change in that case to pi 3, but we're going to remain with those names in the same orbitals as we did with the ground state. We're not changing that. What was the definition of LUMO? Do you remember? Anyone? What was the definition of LUMO? Exactly. It's the lowest energy that doesn't have any electrons. That's why pi 3 in the ground state is going to be my LUMO. Any other questions? It's you have it in the handout actually. It's over here. It's the lowest that should be unoccupied. That's the type on my end. It should be unoccupied. Okay, but let's apply the theory into the next problem, which is going to be with a little cation. Okay, so first of all, remember, yes. Those unoccupied, everything is sp2 in this molecule. Well, it's pi3. That's the lowest in energy that doesn't have any electron. Technically, you have two orbitals that are unoccupied. It's just pi3. That's how we label the orbitals. Okay, maybe doing the next example is going to clarify more of this concept. Yes. No. Okay, we're good to move on. Okay. The longer the wavelength. Yes. It's gonna show the longer wavelength and it's gonna present with the lowest energy overall. You got it. Okay, let's continue with the allyl cation. Okay, so first of all, remember, we only use theory to show any conjugated systems. The definition of conjugated is that everything is sp2. And in this case, remember, I told you carbocations, carbon ions, and radicals, they're all going to contribute to the pi system. They're all going to be sp2. So in this case, I have 1, 2, and 3 carbons that are sp2. Now, let's start drawing out our orbitals, which we know they're kind of going to look like a little 8. Now, how many pi electrons in total do I have? One electron? Just 2 in this case. They're coming from the double bond. Remember, each carbon in the double bond is contributing one of those pi electrons, and then the carbocations are lacking electron density. So that's why it's not going to contribute anything. It just gives us a total of 2 pi electrons. So far, so good? Okay, now, next thing that we have to figure out is the number of orbitals. How can we tell the number of orbitals? What was the rule? Is it related to the number of pi electrons? To the sp2 carbons, exactly. So in this case, we have 3 sp2 carbons, so that means that we have 3 orbitals, which is presented in both ground and excited state. And to find the number of orbitals, that's going to be equal to the number of sp2 carbons that you have in the molecule. In that case, you have 3, so that means 3 orbitals. Number of sp2 carbons equals the number of orbitals. Yes. Triple bonds are always going to be sp, but you're never going to see them in this theory. We're just going to talk about double bonds. So yeah, we're not going to complicate it that much. Okay, so now, once you start drawing out your energy diagram, remember, we always start at the ground state. That's where we define every single orbital. Now, in this case, we have an odd number of orbitals. And remember that one of the rules was that the anti-bonding orbitals have to equal the bonding orbitals. So in this case, I have 1 anti-bonding, 1 bonding. They have to be equal to each other, but I have 1 orbital left over. That left over, that's basically just a space filler, and we just gonna call it a non-bonding orbital. That's only gonna happen whenever we have an odd number of orbitals. Again, just happens with an odd number of orbitals. Yes. Like we saw in the first example. There's only gonna be 1 non-bonding, no more. Okay, now, after we have our diagram, we always start labeling from the bottom to the top. That's why the very first line is just pi1, then we have pi2, and then we have pi3. We're just labeling them. We're just labeling the pi orbitals. That's it. Now, in total, I have 2 pi electrons. Remember, to fill out the energy diagram, we always start from the lowest to the highest in energy. I just have 2 electrons, so I only have 2 lines in pi 1. So far, so good. Any questions so far? We're good? Okay, now, what was the definition of HOMO? It's the highest occupied orbital, so that's why pi 1 is going to be my HOMO orbital. And then LUMO, it's the lowest in energy that's unoccupied. So that's why pi 2 in that case is going to be my LUMO. Now, if I just radiate some UV light into the molecule, that means that I'm going to go from the ground to the excited state. So what's going to happen? To the anti-bonding? Yes, it's always from HOMO to LUMO. So we have 1 in pi 1, and we have the second one in pi 2. Yes. I have no idea. Your professor didn't teach me that, so I'm not sure. Mhm. It's basically wherever we attack, like the SN2 attack, basically that portion. Yes. We're just labeling the orbitals. They don't really mean something in a specific in the molecule. You can label anything pretty much 1, 2, or 3. The important part why we're labeling them is because he could ask you for the most favorable transition. Usually the answer is just HOMO to LUMO, but sometimes he likes to give you the answer choice in pi form. So it could be from pi 1 to pi 4. But the correct answer should be, in this case at least, from pi 1 to pi 2. It's just trying to distract you. Pi 1 to pi 4 wouldn't really happen. I don't know if that could happen at any point. You could ask him a question about that. I'm really not sure about that one. Yes. Question. It's just the way I show, basically. Question. No, it's gonna be assumed that you guys can figure it out on your own. Okay, now let's start with some of the questions that he could possibly ask you. Let's say that we're talking about the excited state. How many electrons am I gonna show in the anti-bonding orbitals? 0. How many electrons am I gonna send in the bonding orbitals during the ground state? 2. How many anti-bonding orbitals do I have? 1. So the questions are gonna be like this. They're just pretty much asking you the information that you can basically just read from that energy diagram. So no, it's gonna be assumed that you guys can do it on the spot. He's just gonna give you the name of the molecule and the choice. That's it. Usually he doesn't draw it out. It's just the name. So it's not that bad. It's not that bad. It's basically just reading the information from the diagrams. So far, questions on that? Okay, now the following chart, you guys can fill it out on your own time. It's just basically reading the information. It's basically the same questions that I just asked. And I will have this filled out in the actual answer. Okay. But again, everything, every single number that you're gonna see in there, it came from that diagram. Okay. It's like the same questions that I just asked. That's it. Yes. It's not because we have 2 pi electrons. Remember, the number of anti-bonding orbitals and the number of bonding orbitals have to equal each other. Okay, so far, questions on the cation. So far, so good. Okay, let's see what's gonna happen with a carbon ion. Hypothetically, I feel like it would be. I feel like, yeah, yeah, yeah. Technically, yes, but actually, he never has showed it. Yeah, don't worry. But yeah, I know that he drew a lot of orbitals today in lecture, and it was probably really confusing, but it's not that bad. You just have to simplify it a little. Okay, it's not that bad. Okay, same process, different molecule. It's sp2 whenever you have three main groups. So remember, sp3, it was whenever you had four groups in total, just single bonds. sp2, whenever you had three main groups, double bonds. And sp was whenever you had two main groups, the triple bonds. It's not going to be that tricky with questions like these. And actually, most of the questions that he's asked so far in this semester is just related to the four molecules that we're doing in SI. So it should be pretty fair game once we get to the actual exam. Okay, now, same process. First of all, how many sp2 carbons do we see? Three, so that means three orbitals. How many anti-bonding? One. How many non-bonding? One, and you only have one bonding as well. Okay, what about the number of pi electrons? How many do we have? Two, four. It gives you two additional ones, exactly. So let's start drawing out our little eights in here. So we know that each of those carbons in the double bond contributes one pi electron, total of two. And then the carbon ion, those two electrons are going to contribute to the pi system. So we have four pi electrons total. Yes. So, oops, that's sp2 equals three orbitals. How many sp2 carbons do you see? How many pi electrons do you see? Four. We have a carbon ion. Yes. Are filled or just one? I think it's just one, but it's one really condensed area. Yeah. Yes. We're not following with that. Okay. So let's just focus on the first step that we just did. First, we figure out the number of orbitals based on the number of sp2 carbons that we have. It's three. First thing that you have to notice is that it's an odd number. Whenever it's an odd number, that means that we have one non-bonding orbital present. So whatever is left over, the two orbitals, they have to be equal to each other. So you have one anti-bonding and one non-bond. Sorry, one bonding. They have to be equal to each other. Anti and bonding equal to each other. Whatever you have left over, non-bonding. There's no non-bonding. Like what we saw with the very first molecule. Had a question over there? We're good? We're so good? Okay, now. If I'm looking at the ground state, how many electrons am I gonna see in pi 3? Zero. What about pi 2? What about pi 1? You always start from the bottom to the top. Always from the bottom to the top. Okay, now. After we have the diagram filled out, now we can see what's going to be HOMO and what's going to be LUMO. In this case, pi 2 should be HOMO because it has at least one electron. More specifically, it has two, and it's the one in highest energy. LUMO is going to be pi 3 because it doesn't have any electrons. Exactly. And they have to be right next to each other. So as long as you're able to find one of them, you should know where the other one is. Okay. If I go to the excited state, what's going to happen? Exactly. Okay, so total. Pi 3 in excited state, how many electrons? Pi 2? Pi 1? Remember, it's not really about the what kind of number you have on the pi orbital. It's about whether you're going from HOMO to LUMO or not. Remember, the excited state always happens between HOMO and LUMO. It doesn't matter what kind of number you have in the pi orbital. Question. Yes. Yeah, it wouldn't make sense to label them in the excited state. Yes. No. It's always going to be right next to each other, at least for this class. I'm not sure if you take another higher chemistry class, it might happen. Not quite sure. Okay, really quickly. How many electrons do we see in the anti-bonding orbital and the ground state? 0. How many orbitals do we have of non-bonding? In either. It's just one orbital, non-bonding. Yes. You always have to be very careful with the actual question. They might ask you for electrons, they might ask for orbitals. Yes. The one in the middle. Yeah. Okay, so that's what the chart is for. Yeah, it's not too bad. It's not too bad. The chart that you see here, after you fill it out, that's how you're able to answer my questions. So yeah, just like a little cheat sheet for you guys. Yes. Technically, yes, but he's not going to be asking label which one is the anti-bonding orbital. Not going to be asking for that. Yes. How many molecules are in bonding? You only have one now. Okay. Are you ready for the next molecule? Okay, the last one is with a radical, and I'm actually going to give you guys 3 minutes to just fill out that energy diagram. And then you guys are going to be answering some questions. You guys can talk to each other, start filling it out on your own. 3 minutes. Maybe yes. Like the carbon ion. You guys can talk to each other. To your left, to your right. I'm too expressive with my face. I just give it away. I can't. Okay, everyone. So, how do we feel about our energy diagrams? Pretty good? Pretty good? Okay. What do you mean last week? Monday, we finished chapter 12. I confused you guys, but I fixed it. I posted an explanation, so just take a look at it. No, yeah, it always trips me out whenever it's that topic because I always follow like either professor and I always get it wrong. So yeah, just make sure that you're focusing on your professor. Dr. West follows 312, Dr. Roach follows 321. So it's a little confusing. Again, we don't know the exact reason why it just happened. So I'm not asking questions. Yes, everything is correct. Everything is posted. You guys should be good. Okay, how many electrons am I gonna see in pi2 in the ground state? Only one. How many pi electrons do I have in total? 3. So let's start filling that out. How many pi electrons am I gonna see in the home orbital in the excited state? Excited, 0. How many pi electrons am I gonna see in the LUMO orbital in the excited state? 1. I was for the excited state for the electrons in HOMO. That one's 0. Remember, the transition is always HOMO to LUMO. Even though HOMO is empty right now, it's still gonna be labeled as just HOMO. Again, everything was based off the ground state, not the excited state. And last one, how many pi electrons do I see in the bonding orbitals in the excited state? It makes sense. It's easy to follow. But any questions on this, on the theory? So far, so good. We don't have any questions. Let's. Oh, and in here you basically have the rules that we were talking about. So it should be pretty simple. So we know that the number of orbitals correlates to the number of sp2 carbons that we have. There you have the definition of HOMO and LUMO. LUMO, it's slightly wrong. Just change that over a U. There we go. And then remember, anti-bonding orbitals have to equal to the bonding orbital. Whatever you have left over is just non-bonding. And that only happens whenever you have an odd number of orbitals. Okay? If you only have one orbital, he's not going to be asking that question. I don't even know the answer to that. And technically, I would assume that it's bonding. It can be a little carbocation. So yeah. Okay. Next question. Actually, I'm gonna let you guys show me the energy diagrams for this molecule. The question is just asking for the most favorable energy transition for 1,3-cyclopentadiene. It's homotolumo, but I want you to give me the exact pi numbers. Is it pi 1 to pi 2? And actually, just for practice, like show me the ground and excited state. Let's see what happens. One three cyclopentadiene. What was the question? It's homotolumo, but specify which from pi 1 to pi 2, pi 2 to pi 3, pi 3 to pi 4. Specify. Draw the molecule. Show me both ground and excited state. chose pi 3. Give him. If that's Homo to Luma, then yes. Okay, so let's start with this molecule. First of all, can anyone draw the molecule? Go for it. Four pi electrons. Four. What is it? 4 electrons? Five. And label Homo and Luma. Bonding? Okay, so great job. First of all, did everyone get the same energy diagram? We all got it? Okay, quick question. How many non-bonding orbitals do I have? 0. It's an even number of orbitals. Exactly. How many bonding orbitals do we see? 2, which means that I have 2 anti-bonding, which I'm just going to label with a little star. So if in this case we're asking for the most favorable energy transition, it's always Homo to Luma. Exactly. In this case, it's from pi 2 to pi 3. If you see any other symbols like sigma, it's just there to distract you. Okay? It's always pi. Yes. He might give you a little sigma bond. I forgot the other symbols that he used. Yes. Yeah, so it just shows you that it's an anti-bonding orbital. That's it. There to distract you. Yeah, I think that at the very right of the page have like 3 different symbols, so just focus on pi. Yes. So Homo Luma, remember, we always find those guys in the ground state. Homo, it's the one that's the highest in energy that has at least 1 electron. So in this case, the one that's highest in energy that has that is going to be this one over here. And then Luma, as long as you're able to find either Homo or Luma, you can figure out where are the other ones because they're always right next to each other. You always start with the ground state. Okay, so far, questions. So far, so good. Yes. Yes. Okay, so far, how do you feel about this theory? Pretty good? It's not that bad. It's just going to be simple questions that he's going to be asking. And no, he's not going to be asking for the energy diagram. You just have to know the specific numbers. Okay, this one. This one should be easy to answer. We talked about this concept before. Number 1. Do we all agree? So let's quickly review this. So this is basically just applying what we did, what we were discussing UV spec, right? Now, UV spec, it basically just shows how conjugated a molecule is. What was the trend? The more conjugation you have, the longer the wavelength. What else? And the lower the energy. So in this case, let's start by looking at each molecule on their own. Molecule 1, what kind of pi system do we have? Conjugated. Molecule 2, conjugated as well. And what other system do we see? And isolated. Molecule 3 is just isolated. Molecule 4. Isolated is just whenever your double bonds are completely far away from each other. The conjugated portion was whenever we had a continuous pair of sp2 carbons, or it pretty much looks like a sandwich. Double bond, single bond, double bond. Okay, molecule 5. What kind of system do we see? Conjugated and isolated. So if they're asking for the longest wavelength, we're looking for the more conjugated molecule, which would be molecule 1. Okay, so far, questions on that? Yes. Four and 5 would be equal to each other. There's basically symmetry in there, so you can flip around that molecule. It's the same one. Between molecules 4 and 2, I would say that maybe molecule, it's slightly more conjugated than molecule 2, but you wouldn't get asked the question like rank them longest wavelength. So no. Okay, so far, questions on that? Yes. So isolated is whenever you have the double bonds completely far away from each other. What was the definition of accumulated? No double bonds? They're right next to each other. Beautiful. Okay. Is a carbon ion going to be considered sp2? A carbon ion. We saw one of the examples actually. So yes, remember carbon ions, radicals, carbocations are all going to be considered sp2. Okay. What's the difference between configuration and conformation? Let's start reviewing. Conformation. You have two options. What are the names? No, that would be configuration. What were the terms that we had to use? Four. Oops. Exactly. We talked about it in here. Very first page. Okay, how do I know that a double bond is really stable? If it's trans, and what else? What else? What if I'm just looking at an individual double bond? How do I know it's really stable besides just being trans? This is gonna come into play for the next concept that we're gonna talk about. Should be extra credit. I'm quizzing you guys. It's actually from the very beginning of chapter 7. We know that double bonds are more stable whenever they have more what? More substituents, exactly. The more argues you have, the more stable the double bond is going to be. And that's going to come into play whenever we talk about our 1, 2, 1, 4 reactions, which is the first set of reactions that we are going to learn. Okay, let me just write it. It's 1, 2, 1, 4 addition reactions. These are nice reactions. They're not too bad. They're not too bad. But first of all, before we talk about any mechanisms or any of that, let's start labeling the actual reagents. What's going to be a nucleophile? What's going to be an electrophile? What is the A? okay, yeah, I'll give you that point. Yes. But basically, yes, that's what we learned during green years, right? Whenever we're talking about like nucleophile versus phase and all of that. Now, it is going to be our nucleophile because it's very electron dense. Okay? And now, addition reactions. It should sound kind of familiar. Like what we saw during chapter 8. Those were addition reactions. We are going to be getting rid of double bonds. So more specifically, we're only going to get rid of one double bond. Okay? And now, the electrophile, it should just be B. Okay, now, as you can see by the name, 1,2,1,4 reaction, we're going to be creating two main products. 1,2 and 1,4. Okay, so before we actually answer those questions, let's start working on the actual mechanism. Over here at the bottom. Okay, so we know this is our nucleophile. This is the electrophile. What do we think is going to happen in here? So, in a way, yes, that's going to create one of our products that we need. So remember, the whole goal is 1,2 and 1,4. First of all, very first step, double bond is going to attack my electrophile. More specifically, it's going to be attacking that hydrogen, so we can take it away, and that's going to break the bond. Great question. Okay, so for 1,2,1,4 reactions, we're always going to be working with conjugated systems. Your position 1, carbon 1, is always going to be the less sterically hindered carbon in the conjugated portion. So technically, the less sterically hindered carbon, the conjugated part. So that would be like, or 1 through 4 counting in this case. And let's keep it in here. 1, 2, 3, and 4. Okay, so in the very first step, we know that the hydrogen gets attached to carbon 1, and then what's going to be on carbon 2? Carbocation, beautiful. And then we have that bromine just floating around, so it's going to be attaching that carbocation, and it's going to get attached there. So that means that I have a bromine in here, and a hydrogen in here. And let's keep labeling our carbons in here. 1, 2, 3, and 4. Now, a hydrogen is always going to get connected to carbon 1, and then we need a halogen connected to either carbon 2 or 4. Remember, those are gold products. So in this case, because bromine is in carbon 2, it's going to be called here 1,2 product. Thank you for reminding me of that. The other double one, it's still there. We didn't touch it. He's not going to be showing you axis for this reaction. He's just testing you for 1,2 and 1,4 products. Okay, so far, which of the molecules is showing the 1,2 product? Let's see. So we just know that. The other one should be the 1 for product, but let's see what's going to happen in the mechanism. Okay, so the reactions are going to start the same way. Double bond attacks, hydrogen always gets to the to the less substituted side. So on carbon 1, 4. Now, notice how wherever my carbocation was, that's where the bromine ended up connecting to, right? Now, if I want to connect it to carbon 4, what do we think is going to happen? It's allylic. So in this case, we're going to be doing some resonance to move the carbocation to position 4. So in this case, we're basically just switching it up. Now the double bond is between carbons 3 and 2. And I have a carbocation and carbon 4 where I want it. This one is not the more stable carbocation. It would be the one from 1, 2. Exactly. Allylic is stable. Vinylic was really bad. Yes. Allylic we love. Vinylic we hate. The resonance form of the molecule, which is also allylic. The transition state is more stable, yes. Exactly. Very first one is a tertiary carbon that's in the allylic position. For the second one, it's a secondary carbocation in an allylic position. Okay. Yeah, there's a lot of L's in there. Okay, so that bromine, we know that it's just going to be attacking that carbocation. So at the end, I have my hydrogen, carbon 1. I have my bromine in carbon 2. And let's label our carbons in here, 3 and 4. We're never going to switch it because always the lesser Gleichender double bond is going to do the first attack. And then because of resonance, that's how we achieve the 1-to-1 full products. So it's gonna be okay. You guys can follow this one. And like your professor said, it's gonna get easier. Okay? And that is the usual trend. It gets easier as we go. That's always a trend, actually. Yes. The average starts going up, yeah. Slowly, but we go up. Okay. So now we know how to get to the 1-2 and 1 for product. We just have 1 minute left, so I'm gonna leave the kinetic and thermal product for next time on Friday. Okay. Dial solder. He started introducing it. Yes. Not too bad. It's not too bad. Don't get scared. No problem. Take care.